2023 higher paper for the double award physics. Formula sheet. First question, we got a graph and then it's asking us to compare emissions of CO2 from both coal and natural gas at a particular year, and it was 2012, I think. So you come up, so we're comparing that one against what's happening up there. So it's going to be 33,000 minus the 9,000 gives you 24,000. Then it's got between 2014 and 15, it fell by that much. And then so we're looking for another time that it fell by that much. Well, we can see, ignore the highlight in there. It's this area here is between the years that they've given us. And then if we just look, you could actually get your ruler and look for the correct gradient. It's exactly the same gradient for exactly the same stretch. So that's going to be the answer there, 2008 and 2009. The benefits of reducing CO2 in the atmosphere is that it's going to decrease climate change, it's going to reduce the global warming. That's your top two answers. And then it's given us some figures here, 50% there, 20%, but it's actually on about CO2 emissions from nuclear power. Well, nuclear power doesn't create any emissions. So you're going to disagree with that statement because the line would be at 0 for nuclear power. So there wouldn't be any emissions. Come on to a little Sankey diagram then. So we've got 500 going in, we've got 315 being wasted. So what's going to be the useful? Well, the useful is going to be 500, the total minus the wasted there. So that's going to give us that. Remember, everything this side is going to add up to all that energy coming out there. So when I do it in my formula, which I find on page 2, it's going to be 185 over 500 times by 100, and that's going to be 37%. So I'm actually disagreeing. It's not 63, it's 37. Oops. Bring that down there. On waves then, we're looking to be drawing wave fronts. So because we're going from shallow to deep, the wave fronts are going to get bigger. So your 3 marks, usually, yeah, it is worth 3 marks there now, is for putting your ruler parallel to this line coming out and then matching them up with the lines. If you do that anyway, you're naturally going to get bigger wave fronts. These wavelengths are going to be bigger. So for 3 marks, we need more than 3 down. We need more than 2 join in at least 1 join in, and then we need them parallel to the line. So they need to be looking like that. Then we come over here. We're still going from shallow to deep. Explain whether you agree with this statement. What's this say? Sam says that the speed of the waves is greater. Yeah, did it say somewhere that frequency is... so the frequency is usually in these questions constant. So I've said it there. It must be somewhere. So if we're using this formula, frequency is constant. If we're increasing the wavelength, then the speed's got to increase, okay? So if you imagine 1 times 10 is 10, well, if 1 times 20 now is 20. So as that goes up as well there. So I'm going to agree with that statement. Question 3 then is on electrical energy. So we've got washing machines use this much. It's going to do 200 washes per year. So, right, okay, so it's only given us one of the equations from the front sheet because the first thing we need to do is to see how many kilowatt hours we've got. So we're going to do the 200 washes times by our kilowatts per hour there, and then we need to times that by the cost. So our answer there, times it by the cost, we get £32.40. As we come down then, we're saying that the mean power units time, the wash cycle lasts for 4 hours. Right, okay, so use the information to calculate the mean power in this. So if that's, if we want to find out the mean power, so if it's 4 hours into our cost the kilowatts per hour there, we're going to find out the mean power. So that's worth 1 mark because it's quite an easy calculation. And that's it for that question. All right. Okay, on to question 4 then, conduction, convection, radiation. This one's just on conduction, but look at it. So the question is, explain how an apparatus is used and how the results are used to... Okay, so the apparatus is used by sticking a flame equally on these bars. What's going to happen is heat's going to transfer each of these bars. You're going to stick a little metal pin on the end with some Vaseline or petroleum jelly, and then the best conductor of heat is the pin is going to fall first. So I've said that for 2 marks. Heat the ends of the rods with a Bunsen flame, and then the first pin drop off of the metal is the best conductor. Describe in terms of behavior of particles. So what is conduction really? That's this question, kind of a definition. Particles vibrate faster and collide with the neighbouring particles, passing on that energy where that flame is. And then you've also got some free electrons moving throughout to pass the energy on as well. This is why metals are really good conductors, because they've got those free delocalized electrons. All right, we do a little bit of convection now. So explain why the coloured water moves. So it's a little bit of a definition for convection. So hot water rises because it becomes less dense, and it's going to displace the more dense. That's going to push back down then and create that cycle. And then we've got a radiator stuck at the top of the wall in a room. Why is it not a good position? Well, hot air rises, and you're not going to get any warmth below that radiator. So a silly place to put it. Okay, let's go to this one then on satellites. Geostationary means that it's going to orbit at the same point sorry, not every time. It's going to just orbit at the same point of the Earth for the whole rotation. So that's why it's above the equator. Because if the Earth is spinning this way, which it does, then the satellite is going to stay with it as it goes round. And that's what geostationary is. Geosynchronous, by the other way, it goes around. It still takes 24 hours, but it's only going to be at the same point every 24 hours. So you've got a signal going up and back. So that means, yes, we've got one of these questions now where we've got a distance and we've got a speed. How long is it going to take? Well, it's going to go there. It's going to take to go there 0.12 seconds. But to go there and back, it's going to have to times it by 2 because it says back again. So that's going to be 0.24 seconds. Then we've got to calculate the maximum frequency of the microwave if... So we've got a range of wavelengths. Always pick the lowest number for when you're given a maximum of something else, because if you picked 1 meter here, then that would give us the minimum frequency required. If you pick the lowest, then that's going to give us the maximum frequency. So what I've done here, I've just put the formula down and I've placed values instead of letters for the formulas. That's going to get me 1 mark straight away. Then I can rearrange that and get my answer. Frequency is smaller, so that means the wavelength is going to be bigger. Well, there's only one bigger than microwave, and that's going to be radio waves. Your 6 marker is on finding the density of a regular shaped object. Well, there's a really good video on that. It's called OMG. Let's talk about finding the density of a regular shaped object, which I go through. But that's pretty much the marks, your 6 marks there. So be familiar with the practical. Always be familiar with the practicals. Question 7 is on circuits. So you've got parallel circuit there. So we've got to find the resistance in just this bit. So the resistance, you're going to use this formula. And then the bit that students keep forgetting is to make sure, because what you're finding on this bit is 1 over R total. But to find R total, you need to do the reciprocal again. So it's going to be 1 over 0.25. Here's a quick tip for you as well. Whatever the answer comes out to be, it's always going to be on the bottom. If your answer comes out as a fraction, it's always going to be that number there to match up with that, okay? Then the total resistance, well, now what we've found is we've got 4 ohms there, and it's telling us we've got 2 ohms there. So now it says use a formula from page 2, but really, if you know that the resistance, yeah, I guess you could use it, yeah. So it is this formula, so R1 plus R2 gives us total R. Well, in this case, it's saying it's got 6 ohms across it. So if we've got 4 here, 4 plus something gives us 6, and that is going to be 2. So 4 plus 2. or 6 minus 4 there. Use an equation on page 2 to calculate the current. So we've got voltage over resistance. Our voltage is 9, and our resistance, total resistance, it told us in the question, is 6. And there's my 9 up there, okay. On to the next page then, calculate the voltage across the resistor 3. So what we're going to do is going to use that current that we found, and we're going to use the resistance that we found, and we're going to times that together now because it's a little bit of a rearrangement. I've been quite naughty. I've rearranged it before because I think it appears like that in your equation sheet. Does it? Let's have a look. How does it? Yes, it does. So, yeah, I've been a little bit naughty there, and I've rearranged it to get VIR. That's how I remembered it anyway. V equals IR, V. So, yeah, it's just a 1.5 times 2. So your total current there across that resistor, because the current is the same everywhere in a series circuit. And then we've got a bunch of figures here. So I've actually picked these out to make life easier for myself. Now I can see I've got an E and a T. And she's claiming that it would transfer 45 joules with 4.5 amps in a time of 10 seconds. So let me find the power, because these two, they're the only two that work together. Like, you're not going to find an equation with I and E. You're not going to find an equation with I and T, but you do find an equation with ET, and that's PET or EPT there. That's found in the front sheet. So I'm going to fill in the blanks. My energy is 45. I don't know my power, but I got a time of 10. That gives me 4.5 watts. Now that I know my power, I can actually link it with this current to find my voltage. Okay, so not my voltage, because I know my voltage is 9. I'm going to check whether her claim is correct by using that. So I'm going to find out for I. So I'm going to calculate for I. So 4.5 now, which is my power, over my 9, which is my voltage, equals 0.5 amps. Well, she reckons 4.5 amps is going to give us that. Well, actually, only 0.5 amps is needed to give us that. If we had that much amps, we get a lot more power. So I disagree, because I've said it would generate 4.5 watts would generate, 0.5 amps would generate more than 4.5 watts. That's it. So 4.5 watts would generate more. And I can actually prove that in a little equation. So if your voltage is constant, which it is in this case, if I increase my amps, I need to increase my power using that equation there. Nearly there then. Question 8. Germany is building the world's first system in which turbines, blah, blah, blah. Okay. Why is using wind not good? Because it's unreliable. It's not always windy, for 1 mark there. Okay, I remember this one now. This one, you've really got to look for this value by here, especially for the next question. So you got, that is hydroelectric, can do 16 megawatts. And then, but the mean, so each house used 0.45 kilowatts in 2017. It's just a possible reason why it's only this figure and then lower than previous years. Well, it might be that appliances got more efficient, so require less energy. It could be now we're using LED lamps, so require less energy. We're insulating homes better, so using less energy. It could be any one of those, okay, for 1 mark. For 3 marks then, now it wants you to calculate the number of homes in Germany that could be powered using hydroelectric. So from the last page, remember we picked out 16 megawatts. We know that 1 home uses 0.43 kilowatts. Now, there's 2 ways you can do this. I guess in year 10, you just need to be aware that a kilowatt is 1,000 watts and a megawatt is a million watts. So you need to either convert the 0.43 to megawatts or the 16 megawatts to kilowatts. And that's the easiest thing, I think, to take that up one. So I've got, I want to see how many homes can be powered by that much energy, which is this number. However, if you're clever, and what we do in A-level a lot as well, is just use this first sheet. And I think this is probably an easier way, where you've got these prefixes and these symbols by here. So a kilo is times 10 to the 3. The mega is times 10 to the 6. And I literally just put those values next to the numbers it gives me. And we do that a lot in A-level because you haven't got time really to convert back and forth. So you're just going to use the 16 because it's a megawatt to the power of 6. And then you've got 0.43 times 10 to the power 3 because it's a kilowatt. And if you type that into the calculator, you come up with exactly the same answer. The wind turbines have a maximum power of 13.6 megawatts now. All right, so what is it saying? It's saying science is possible greater power. So the greatest power from the hydroelectric pump storage. Well, saying that anything is going to give you the greatest power is a little bit, it's like, because they both will give the same power eventually, but it's a matter of how quick they can do them. So how quick they can give you that power. So this question has been a funny, and it's got highlighted in the exam board as being a funny question as well, because the question itself is not really clear in what it's asking. What they're trying to see is if you can identify that time is the issue. So if energy transferred is the same for both, and we use E equals PT, a higher power will give a lower time. So we can see that if the energy is constant, if I increase the power, then the time's got to decrease. It's just got to, right? So it's like 1 times 10. If I'm going to increase this to 2, that's going to be 2 times 5. So this has gone down because that's gone up. If this is constant, right? Therefore, the same amount of power can be generated from both, but it's going to take longer for the turbines to generate it. Okay, so and that's the really important thing. It's not so per second. If they want it per second, then yes, okay, that is going to be true for the hydroelectric if it's going to be per second. But the problem is, and I can't see it, there's nothing to say per second there. So pump storage, power, yeah, bit of a tricky question. But anyway, if you've got any other questions on any of the questions, make sure you see your teacher. If not, hopefully this has been useful to you. Thank you for listening.